Okay, let us continue from the previous video where we left. So, we will now be talking about certain generic lemmas or theorems about the delta network, or in that sense it is actually true for any Banyan network. And so, we start with the lemma 1. So, this says that in a 2 by 2. So, remember I am actually now talking about the delta of Banyan network constructed out of 2 by 2 crossbars. Okay. So, in a 2 by 2 network, so of course I am writing delta, but it is also valid even for a Banyan configuration. There is a unique path from each network input to each So, this is basically also the definition of a Banyan network. So, we can actually prove it also very easily in our construction. So, proof goes that there are 2 raised power n paths from each input. To all outputs. So, what does it actually mean is that you have one input and there are 2 raised power n outputs, it is a 2 raised power n by 2 raised power n delta. So, there has to be 2 raised power n paths from an input to this, then only there can be a connection which is there. Okay. Now, in this case the first node actually has only 2 positions, either it can be cross or bar. So, you can connect from here to here. So, this first stage it is only able to go to 2 ports, next stage will have again 2, and I think we will never ever be actually having a situation where these 2 output ports is going to be connected to the same switch, they have to be connected to different switches. So, this will be connected to now 2 switches here, which in turn will give me 2 raised power 2 square number of ports which can be reached. Then if I go in this fashion, the third stage will give me 2 cube. So, by the time I reach the nth stage, this will give me 2 raised power n. Okay. So, there are only 2 raised power n possible outgoing ports, and there is going to be exactly one path from each input to each output. Okay. So, that is from this input there is going to be exactly one path to each one of the outputs, because every time I can only create fork out onto 2 things and I am creating a new path. So, I am able to generate only 2 raised power n paths from an input. This is true for all other inputs also. That is why this particular statement that in a 2 raised power n by 2 raised power n delta network there is a unique path actually holds true. So, whatever is true for this input is also true for all other inputs, and henceforth this lemma stands proved. Okay. So, whatever I have stated that actually need to be written here as a proof, but I am not doing that because it is supposed to be explained. So, you can write down that statement and then of course consequently this will get proved, or maybe I can write it down. So, we can write in this fashion. So, input is connected to only one node in first stage, and this node has two positions. So, essentially it creates two paths, and each of these positions can connect to two nodes in second stage, and each of these two nodes will also have two position, since there are n stages. Two raised power n possible paths will be there. And since there are 2 raised power n outputs, and 2 raised power n possible paths, so outputs and each of the path should have unique one to one correspondence. Each input should be connected to each output through unique path. This also has an implication, because from here there is 2 raised power n paths, there are 2 raised power n inputs. So, total number of possible paths which can exist will be 2 raised power n into 2 raised power n. Okay. So, this turns out to 2 raised power 2n number of paths which exist in total. So, from here the lemma 1 is done. So, let us go to the theorem 1. This again is for the same 2 raised power n by 2 raised power n delta network. So, whatever we have already understood, I am just formally writing it actually. So, theorem 1 says that you consider a switch m in stage Sk of a 2 raised power n by 2 raised power n delta network with 0 less than k less than n. Okay. So, stage is going to change from stage 0 S0 to Sn minus 1, total n stages. Okay. So, there is no equality being put here because of that. Now, let Ix Ox. So, I stands for input, O stands for the output. So, Ix and Iy and Oy be input. So, whenever I talk about Ox, Oy, these are output. When I talk about Ix and Iy, these are inputs. So, what is actually happening is the middle stage, any switch, if this one is Sk stage, if this one is an Sk stage, so there are two inputs and there are two outputs. So, I call this one as Ix, I call this as an Iy. Okay, I can talk about Ox and Oy. So, these are the inputs. So, you can take any switch. So, this one is the Skth stage and some switch. So, any one of these can be taken. So, because whatever assumptions we will be taking is actually going to be true because of that. So, input and output links of M. So, sorry, this has to be in. Then we define let Ix, this is set actually now, Ox. So, this is output set, I will define, I will explain what is it. Set of input, in fact set of network input or outputs corresponding to Iy and Oy. What does it actually mean is that if I look at this actually is being connected to some switch which must be having two inputs which is connected to further switches and so on. So, ultimately this will be now mapping on to certain inputs of the switching network, delta network. So, this set I define as Ix. The second input will also be again connecting to multiple switches. So, this set of inputs I define as Iy. Similarly, when I look at this, this is connecting to some switches, this must be further connecting to some switches and so on. So, ultimately I will have at some place the outputs I call it O of x and some output I call it O of y. Of course, you can notice that I have drawn them to be separate, there is no common element between them, that is one of the statements of the theorem actually. So, that is the way I have, that is the reason why I have drawn it this way. So, once this is true, then Ix or Ox, remember this is a set, okay. This is a small o and these are the capital O, I think I should make it bigger, and are disjoint. Okay. Now, this is true because when you whatever is true in the forward direction, these are connecting to two different switches, this is connecting to two different switches. Okay. So, this is like a demultiplexer tree. So, ultimately it is going to go to one set, it is going to go to another set and these two sets have to be disjoint. This is also true in the reverse direction, okay, same way. So, Ix and Iy has to be disjoint. So, this follows from the lemma which we had done. Further, the B statement goes that number of elements in set Ix and set Iy should be same, and this has to be equal to 2 raised power k, and Ox Oy, that is a cardinality of the two sets Ox Oy, this should be equal to 2 raised power minus 2n minus k minus 1. So, this actually can be understood in this fashion, that this is the kth stage and this is the 0th stage. Okay. So, from here when I go, I get two inputs to here. When I go to this stage, I get this one will become 2, this 2 will become 4, and so on. Okay. So, you count from here. So, there has to be S0 to Sk minus 1. So, there is Sk minus 1. So, the number of stages which are present here are k stages. So, this one input will fork out into 2 and ultimately 2 raised power k inputs here. So, Ix cardinality has to be 2 raised power k. Using same logic, cardinality of Iy also has to be 2 raised power k. Going into the forward direction, the last stage will be S of n minus 1. Okay, that is the way we have defined that k can go till maximum of n minus 1. So, this one will fork out into 2 after that. So, how many stages are there after Sk? So, this is n minus 1, I reduce this k out of it. So, n minus 1 minus k. So, those many, not 2 raised power that much. So, count the stages after this and 2 raised power that. So, that is what is being written, 2 raised power n minus 1 minus k. So, cardinality of the outgoing sets, output port sets, this is 2 raised power n minus 1 minus k, 2 raised power n minus 1 minus k. So, both will be equal sets. So, that is a second statement. This also follows from the lemma 1. Now, the next statement, okay, let me write it here itself. Say a path from any input network, any network input. So, when I talk about network input, I am talking about whatever are the input coming to the network, basically for the S0 stage. Whenever I talk about network output, I am talking about Sn minus 1 stage, the output coming out of those switches. So, when a path from any network input in union of Ix union Iy to network output in Ox union Oy must pass through switch M. So, this also comes from the lemma because this is connecting to these switches. So, no other switch here will be connecting to these ones. This particular set is only reachable from here, from nowhere else. This is the demultiplexer tree technically which we are creating. So, if you look at another switch, this is going to go to a different set, another switch is going to go to a different set. Okay. So, they will not be mapping onto the same set actually. No, they cannot map to uniquely to the same set. So, the moment if you look at this and this, any member from here want to connect here, it has to go to this switch only, there is no other option. Okay. So, that also comes from lemma 1, and the D part which is that exactly (2 raised power n plus 1) paths from network links, network inputs to network outputs will pass through switch M. So, you can see total number of elements which are here are 2 raised power 2k, total number of elements which are here is 2 raised power 2 into n minus 1 minus k. So, from here to here how many total number of connections which you can set up, you have to just simply multiply, which will give me 2 raised power 2k into 2 into n minus 1 minus k. Sorry, this numbers have to be multiplied, so this will be added actually. So, this will give me 2 raised power 2 into n minus 1. Okay. So, this has to be multiplied by 2. So, this is one set, this is a total set, I have to add these two. So, once I add, so I am technically multiplying by 2. So, this will turn out to be 2 raised power n minus k. Same I have to do here. So, I have to multiply it by 2. So, this will not be, this thing has to be 2. So, this will become 2 raised power k plus 1. So, when I will do it here, when I am actually taking this into this, so it will be total number of possible paths which can exist. It will be 2 raised power k plus 1 plus n minus k, so which will give me 2 raised power n plus 1. So, these many number of paths are possible from a single switch, and how many switches are there? These will be 2 raised power n minus 1, these many switches are present in a stage. So, total number of paths which can actually exist is simply nothing but multiplication of these two. So, this will give me 2 raised power 2n. Okay. Right, 2 raised power 2n, and of course, what we have computed as total number of possible number of switches will be possible number of paths which can exist, that depends, a mapping from input to output will be given by this total possible paths which are there. So, that is a theorem 2, and all this is directly as a consequence of lemma 1. So, using demultiplexer tree concept, the proof actually comes from there.